Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
James Clerk Maxwell stands as a towering figure in the history of science, a name synonymous with electromagnetism, yet his intellectual breadth extended far beyond a single field. Born in Edinburgh, Scotland, in 1831, Maxwell's early life was steeped in an environment that prized both practical ingenuity and intellectual exploration. His family estate at Glenlair, in the Scottish countryside, provided a space for unfettered curiosity and a deep connection to the natural world, elements that would profoundly shape his scientific trajectory. Scotland during the 19th century was a hotbed of scientific and philosophical inquiry. The Scottish Enlightenment, although past its zenith, had left a lasting legacy of rigorous empiricism and a commitment to understanding the underlying principles governing the universe. Universities like Edinburgh and Glasgow were centers of excellence, attracting some of the brightest minds in Europe. This vibrant intellectual climate provided the fertile ground in which Maxwell's extraordinary talents could flourish. His formal education began at the Edinburgh Academy, though initially he was considered a somewhat slow and unconventional student. This perception, however, masked a mind already grappling with complex ideas far beyond the standard curriculum. He possessed an insatiable curiosity, constantly questioning and seeking deeper understanding. His true intellectual awakening occurred when he began to pursue his own independent studies, devouring books on mathematics, physics, and engineering. Even as a teenager, Maxwell demonstrated a remarkable aptitude for mathematics, particularly geometry. At the astonishing age of 14, he wrote his first scientific paper on the description of oval curves and those having a plurality of foci. This paper, presented to the Royal Society of Edinburgh in 1846, showcased an impressive command of geometric principles and a novel approach to defining oval shapes using mechanical linkages. The sophistication of this early work is truly remarkable. He explored the properties of ellipses, hyperbolas, and other curves, devising ingenious methods for their construction. The paper reveals a mind deeply engaged with the elegance and precision of mathematical reasoning. It is a testament to his precocious genius that he was able to produce such original work at such a young age. This early foray into geometric analysis foreshadowed his later ability to synthesize complex physical phenomena through mathematical formalisms. Following his early education, Maxwell attended the University of Edinburgh at age 16, a common practice at the time. He immersed himself in the study of mathematics, physics, and natural philosophy, attending lectures by prominent figures such as James Forbes, a leading expert on heat and glaciers. Forbes's work on heat transfer, in particular, would later resonate with Maxwell's own investigations into the kinetic theory of gases. The university provided a stimulating environment, exposing him to cutting-edge research and fostering his intellectual independence. After 3 years at Edinburgh, Maxwell moved to the University of Cambridge, entering Peterhouse College before transferring to Trinity College, where he felt the intellectual atmosphere was more conducive to his studies. Cambridge, with its emphasis on rigorous mathematical training and its rich tradition of scientific inquiry, proved to be the ideal environment for Maxwell to hone his skills and develop his unique approach to physics. He excelled in his studies, graduating with a degree in mathematics in 1854. Maxwell's time at Cambridge was pivotal in shaping his scientific career. He benefited from the guidance of exceptional mentors and collaborators, engaging in lively discussions and debates that sharpened his thinking. He immersed himself in the works of the great mathematicians and physicists of the past, including Isaac Newton, Joseph Louis Lagrange, and Michael Faraday. He began to develop a distinctive style of scientific inquiry, characterized by a deep understanding of both theoretical principles and experimental techniques. It is important to recognize that Maxwell's genius transcended mere problem solving. He possessed a rare ability to see connections between seemingly disparate phenomena, to identify underlying patterns and unifying principles. His approach was characterized by a profound intuition, a capacity to grasp the essential nature of a problem, and to formulate elegant mathematical solutions. This intuitive grasp, combined with his rigorous mathematical training, allowed him to make groundbreaking contributions to a wide range of scientific fields. The central thesis of this exploration centers on Maxwell's profound ability to synthesize disparate fields of physics through the power of mathematical formalisms, leading to revolutionary insights that continue to shape our understanding of the universe. He was not merely an experimentalist, nor was he solely a theorist. He was a master of both, seamlessly blending empirical observation with mathematical deduction to create a unified and coherent picture of the physical world. This ability to bridge the gap between theory and experiment was a hallmark of his genius. This essay will delve into four major areas where Maxwell's contributions were particularly transformative. First, his work on color vision, where he developed a quantitative understanding of human color perception and laid the foundation for modern colorimetry. Second, his development of the kinetic theory of gases, which revolutionized our understanding of the behavior of gases at a molecular level and paved the way for statistical mechanics. Third, his crowning achievement is his theory of electromagnetism, which unified electricity, magnetism, and light into a single, elegant framework. Finally, his work on control theory, specifically his analysis of governors, which provided important insights into the stability of feedback systems. These four areas, while seemingly distinct, are united by a common thread of Maxwell's ability to apply mathematical reasoning to solve fundamental problems in physics. He saw mathematics not as an abstract discipline, but as a powerful tool for understanding the natural world. He used mathematical models to describe physical phenomena, to make predictions, and to test his theories against experimental data. This approach, which is now commonplace in physics, was relatively novel in Maxwell's time. He helped to establish mathematics as the language of physics, transforming the way scientists approach the study of nature. His legacy extends far beyond specific discoveries. He left an enduring mark on the scientific landscape, shaping the course of physics for generations to come. His work continues to inspire scientists and mathematicians to this day, and his ideas remain as relevant and insightful as when they were first conceived. He stands as a testament to the power of human intellect, a beacon of scientific curiosity, and a true visionary whose contributions have profoundly shaped our understanding of the universe. The following sections will explore each of these contributions in detail, revealing the depth and breadth of Maxwell's genius and its lasting impact on science and technology. Maxwell's intellectual curiosity extended beyond the abstract realm of mathematical physics, delving into the intricacies of human perception and the behavior of matter at its most fundamental level. His work on color vision and the kinetic theory of gases stands as a testament to his remarkable ability to bridge disparate fields, applying rigorous mathematical analysis to unravel complex phenomena. These investigations, while seemingly distinct, share a common thread: a quest to understand the underlying principles governing the world around us, whether it be the subjective experience of color or the objective motion of molecules. The understanding of color vision presented a significant challenge in the mid-19th century. While it was known that white light could be decomposed into a spectrum of colors, the precise mechanisms by which the human eye perceives and distinguishes these colors remained a mystery. Prevailing theories were largely qualitative, lacking the quantitative rigor that Maxwell sought. He recognized the need for a more systematic approach, one that could translate the subjective experience of color into objective, measurable quantities. Maxwell embarked on a series of meticulous experiments using a device known as a color top. This ingenious apparatus allowed him to mix different colored pigments in varying proportions, creating a wide range of hues. By having observers match the color produced by the spinning top to a known reference color, he could quantitatively assess the relationship between the mixture of pigments and the perceived color. These experiments formed the basis of his quantitative theory of color vision, a groundbreaking achievement that laid the foundation for modern colorimetry. Its key insight was that any color could be matched by a mixture of three primary colors, typically red, green, and blue. This principle, known as trichromacy, is based on the existence of three types of cone cells in the human eye, each sensitive to a different range of wavelengths. Maxwell's experiments provided strong evidence for this theory, demonstrating that the perceived color is determined by the relative stimulation of these three types of cones. He developed a mathematical framework to represent colors as points in a three-dimensional space, where the coordinates correspond to the amounts of each primary color needed to match the target color. This color space, also known as the Maxwell color triangle, allowed for the precise specification and reproduction of colors, paving the way for advancements in various fields. The impact of Maxwell's work on color vision extended far beyond the laboratory. His quantitative approach to colorimetry had profound implications for photography. The development of color photography relied heavily on the principles of trichromacy that Maxwell had established. By taking three separate photographs of a scene through red, green, and blue filters, and then combining these images using appropriate color dyes, it became possible to reproduce the original colors with remarkable accuracy. This breakthrough revolutionized the field of photography, transforming it from a monochrome medium to a vibrant and lifelike representation of the world. The textile industry also benefited greatly from Maxwell's color theory. The ability to precisely specify and reproduce colors became essential for the mass production of textiles with consistent and accurate hues. Maxwell's colorimetry provided the tools needed to achieve this level of control, enabling the creation of standardized color palettes and the efficient matching of colors across different batches of fabric. This had a significant impact on the efficiency and quality of textile manufacturing, contributing to the growth of the industry. Simultaneous to his exploration of the human perception of color, Maxwell turned his attention to the seemingly chaotic world of gases. At the time, the behavior of gases was understood primarily through macroscopic properties such as pressure, volume, and temperature. The kinetic theory of gases sought to explain these macroscopic properties in terms of the microscopic motion of individual molecules. However, the sheer number of molecules in even a small volume of gas posed a formidable challenge. How could one possibly describe the motion of each individual molecule and relate it to the overall behavior of the gas? Maxwell's genius lay in his ability to apply statistical methods to this problem. He recognized that it was impossible to track the motion of every single molecule, but that it was possible to describe the distribution of molecular velocities. He derived a mathematical expression, now known as the Maxwell distribution or Maxwell-Boltzmann distribution, that gives the probability of finding a molecule with a given velocity at a given temperature. This distribution shows that the velocities of molecules in a gas are not all the same, but rather are distributed according to a bell-shaped curve. The peak of the curve corresponds to the most probable velocity, while the tails of the curve represent molecules with higher or lower velocities. The derivation of the Maxwell distribution was a remarkable achievement, representing a significant departure from the deterministic views of classical physics. Prior to Maxwell's work, physicists generally believed that the behavior of physical systems could be predicted with certainty, given sufficient knowledge of the initial conditions. However, the kinetic theory of gases introduced an element of randomness and uncertainty. The Maxwell distribution describes the probability of finding a molecule with a certain velocity, but it does not predict the velocity of any particular molecule with certainty. This marked a shift towards a more statistical and probabilistic understanding of the physical world. The significance of the Maxwell distribution extends far beyond the kinetic theory of gases. It became a cornerstone of statistical mechanics, a branch of physics that deals with the statistical behavior of large numbers of particles. Statistical mechanics provides a powerful framework for understanding the properties of matter in terms of the microscopic interactions between its constituent particles. The Maxwell distribution is used in a wide range of applications, from calculating the rates of chemical reactions to understanding the behavior of plasmas. Maxwell's work on the kinetic theory of gases challenged the prevailing deterministic worldview in physics. By introducing statistical methods, he demonstrated that the behavior of complex systems could be understood even without knowing the precise details of every individual component. This approach paved the way for the development of quantum mechanics, which further embraced the probabilistic nature of the universe. Today, color science continues to play a crucial role in digital imaging, display technology, and various other fields. The principles of trichromacy and colorimetry, pioneered by Maxwell, are fundamental to the accurate reproduction of colors in digital devices. The Maxwell-Boltzmann distribution remains a cornerstone of statistical physics, providing essential insights into the behavior of matter at the molecular level. These contributions stand as enduring testaments to Maxwell's intellectual prowess and his profound impact on our understanding of the world. The exploration of electromagnetism constitutes perhaps the most significant chapter in James Clerk Maxwell's scientific career. Prior to Maxwell's groundbreaking work, the understanding of electricity and magnetism existed as a collection of seemingly disparate phenomena. Michael Faraday's experimental investigations had revealed the intimate connection between these forces, demonstrating that a changing magnetic field could induce an electric current, a principle known as electromagnetic induction. These experiments, while revolutionary, lacked a comprehensive theoretical framework to unite them under a single set of principles. Scientists possessed a patchwork of empirical laws, but a unified theory capable of predicting new phenomena and explaining the fundamental nature of electromagnetic forces remained elusive. Maxwell embarked on a mission to synthesize these existing laws into a coherent mathematical structure. He began with the established laws of electromagnetism, Gauss's law for electricity, which relates the electric field to the distribution of electric charges, Gauss's law for magnetism, which asserts the absence of magnetic monopoles, Ampere's law, which describes the magnetic field generated by electric currents, and Faraday's law of induction, which quantifies the relationship between changing magnetic fields and induced electric fields. These laws, formulated independently, appeared complete in their respective domains. However, Maxwell recognized a crucial inconsistency within Ampere's law. Ampere's law, in its original form, stated that the line integral of a magnetic field around a closed loop is proportional to the electric current passing through the loop. While this law held true for steady currents, Maxwell realized that it failed to account for situations involving changing electric fields. Specifically, he considered the case of a capacitor being charged. According to Ampere's original law, the magnetic field around the wire leading to the capacitor would depend on whether the surface used to calculate the current passed through the wire or through the space between the capacitor plates. This ambiguity implied a violation of the fundamental principle of conservation of charge. To resolve this inconsistency, Maxwell introduced a revolutionary concept, the displacement current. He postulated that a changing electric field produces a magnetic field behaving in a manner analogous to a real electric current. This displacement current is proportional to the rate of change of the electric flux through a given surface. By adding this term to Ampere's law, Maxwell created a modified version that was consistent regardless of the surface chosen. The modified Ampere's law now stated that the line integral of the magnetic field around a closed loop is proportional to the sum of the electric current and the displacement current passing through the loop. The introduction of the displacement current was a stroke of genius that had profound implications. It not only resolved the inconsistency in Ampere's law, but also paved the way for the prediction of electromagnetic waves. By combining his modified version of Ampere's law with Faraday's law of induction, Maxwell derived a set of equations that described the propagation of electromagnetic disturbances through space. These equations, now known as Maxwell's equations, are a cornerstone of classical electromagnetism. Maxwell's equations predicted that electromagnetic waves could exist propagating through space at a finite speed. This speed, determined by the constants appearing in the equations, namely the permittivity and permeability of free space, could be calculated. When Maxwell performed this calculation, he arrived at a value that was remarkably close to the measured speed of light. This astonishing result led him to a revolutionary conclusion: light is an electromagnetic wave. This unification of light and electromagnetism was a monumental achievement in physics. It demonstrated that two seemingly distinct phenomena were, in fact, manifestations of the same underlying force. Maxwell's theory not only explained the nature of light, but also predicted the existence of other electromagnetic waves, such as radio waves, microwaves, and X-rays. These predictions were later confirmed experimentally, solidifying Maxwell's place as one of the greatest physicists of all time. Maxwell's equations are a set of four fundamental equations that describe the behavior of electric and magnetic fields. They can be expressed in both integral and differential forms. In their differential form, there are 1. Gauss's law for electricity, divergence of E equals rho divided by epsilon naught, where E is the electric field, rho is the charge density, and epsilon naught is the permittivity of free space. Gauss's law for magnetism, divergence of B equals 0, where B is the magnetic field. 3. Faraday's law of induction, curl of E equals negative dB dt, where E is the electric field, B is the magnetic field, and T is time. Ampere Maxwell's law curl of B equals mu naught times J plus mu naught times epsilon naught times dE dt, where B is the magnetic field, mu naught is the permeability of free space, J is the current density, E is the electric field, and T is time. These equations encapsulate the fundamental relationships between electric and magnetic fields, electric charges, and electric currents. They govern the behavior of all electromagnetic phenomena, from the propagation of radio waves to the interaction of light with matter. The impact of Maxwell's equations on modern technology is immense. Radio communication, radar, and fiber optics are all based on the principles of electromagnetism described by Maxwell's theory. Radio waves, predicted by Maxwell, are used to transmit information wirelessly over long distances. Radar, which utilizes the reflection of electromagnetic waves to detect objects, is essential for air traffic control and weather forecasting. Fiber optics, which transmit information using light signals, rely on the principles of total internal reflection, a phenomenon explained by Maxwell's theory. The problems of Maxwell's time included the inconsistencies in existing electromagnetic laws and the absence of a comprehensive theory to unify electricity, magnetism, and optics. Maxwell's unique solutions involve the introduction of the displacement current, which resolved the inconsistencies and paved the way for the unification of these seemingly disparate phenomena. His mathematical framework provided a complete description of electromagnetic phenomena, allowing for the prediction of new phenomena and the development of new technologies. Today, Maxwell's equations are used in a wide range of applications, from the design of antennas and waveguides to the development of new materials with tailored electromagnetic properties. The principles of electromagnetism are essential for understanding the behavior of electronic devices such as transistors and integrated circuits. Maxwell's legacy continues to shape our understanding of the physical world and drive technological innovation. Maxwell's intellectual curiosity extended beyond electromagnetism and statistical mechanics, encompassing the burgeoning field of control theory. The mid-19th century witnessed the widespread adoption of steam engines in industry, yet these powerful machines were often plagued by instability. Maintaining a constant speed, particularly under varying loads, proved a significant engineering challenge. The problem centered on the governors, devices designed to automatically regulate the engine speed by controlling the steam supply. These early control systems frequently exhibited oscillations, hunting for the desired speed or even runaway behavior, leading to inefficient operation and potential damage. Maxwell tackled this practical problem with his characteristic mathematical rigor. He recognized that the behavior of a governor could be described by a system of differential equations, a set of equations that relate a function with its derivatives. These equations capture the dynamics of the system, including the inertia of the rotating parts, the forces exerted by the governor arms, and the feedback mechanism that linked the engine's speed to the steam valve. His approach was innovative in its application of mathematical techniques to analyze the stability of a physical system. Previous attempts to design governors relied primarily on empirical methods involving trial and error adjustments. Maxwell, however, sought a more fundamental understanding of the underlying principles. He aimed to determine the conditions under which the system would remain stable, meaning that it would converge to a desired speed without excessive oscillations. Maxwell's analysis led to the formulation of a stability criterion, a mathematical condition that could be used to predict whether a given governor design would be stable. This criterion involved examining the roots of a characteristic equation derived from the system's differential equations. If all the roots had negative real parts, the system would be stable. If any root had a positive real part, the system would be unstable. This work on governors, published in 1968, marked a pivotal moment in the development of control engineering. It provided engineers with a powerful tool for designing and analyzing feedback control systems. Maxwell's stability criterion allowed them to predict the behavior of a governor before it was even built, reducing the need for costly and time-consuming experimentation. The impact of this work extended far beyond steam engines. The principles of feedback control are fundamental to a wide range of engineering applications, from aircraft autopilots to chemical process control. Today, control theory plays a crucial role in modern robotics and automation. Robots rely on feedback control systems to maintain their position, track trajectories, and interact with their environment. Automated manufacturing processes use control systems to regulate temperature, pressure, and flow rates, ensuring consistent product quality. The algorithms that govern these systems are based on the same fundamental principles that Maxwell elucidated in his analysis of steam engine governors. The ability to mathematically model and analyze the stability of dynamic systems remains a cornerstone of modern engineering practice, a testament to Maxwell's enduring influence. Maxwell possessed a rare ability to synthesize diverse fields of physics through the power of mathematical formalisms. He demonstrated this talent repeatedly, from his work on color vision to his kinetic theory of gases and his groundbreaking theory of electromagnetism. He saw the underlying connections between seemingly disparate phenomena and developed mathematical frameworks that could explain and predict their behavior. His equations, a concise and elegant set of mathematical statements, unified electricity, magnetism, and optics into a single, coherent theory. These equations not only explained known phenomena, but also predicted new ones, such as the existence of electromagnetic waves. This prediction led to the development of radio communication and a host of other technologies that have transformed our world. Maxwell's work on statistical mechanics provided a fundamental understanding of the behavior of gases and other systems with a large number of particles. He showed how microscopic properties, such as temperature and pressure, could be related to the microscopic motions of individual molecules. This work laid the foundation for modern thermodynamics and statistical physics. Even his analysis of control theory, often overlooked in summaries of his achievements, exemplifies this remarkable ability to apply mathematical tools to solve practical problems and gain deeper insights into the behavior of complex systems. He transformed the design of steam engine endeavors from an empirical art into a science based on mathematical principles. The lasting impact of Maxwell's work on our understanding of the physical world and its technological applications is undeniable. His equations are a cornerstone of modern physics, taught to every student of electromagnetism. His ideas about statistical mechanics are essential for understanding the behavior of matter at the atomic and molecular level. His contributions to control theory continue to influence the design of automated systems. It is fitting to reflect on the enduring legacy of James Clerk Maxwell as one of the greatest physicists of all time. His ability to synthesize diverse fields, his profound insights into the nature of light and matter, and his mastery of mathematical formalisms have profoundly shaped our understanding of the universe. His influence on the development of modern physics is immeasurable, and his work continues to inspire scientists and engineers today. He stands as a towering figure in the history of science, an exemplar of intellectual curiosity, mathematical rigor, and the power of theoretical physics to unlock the secrets of the natural world.
We really appreciate you tuning into this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.